Hello. In this video, I'm going to be using the program DD to fit a particular deer data set we've obtained from a T4 lysozyme sample. The results correspond to those in Figure 1 and Tables 1 and 2 of our Journal of General Physiology paper. And I'm going to be using DD version 7C, which is available on GitHub. Okay, to use DD, I've first opened up MATLAB, and I'm going to navigate to the folder where I've installed the program DD. I've downloaded it from GitHub. I'm going to run DD, and it will open up a GUI window. And I'm going to have to drag windows that open up. I'm using another screen, a second monitor, so I'm going to have to drag the windows over from that second monitor to get them in the screen for the window, for the movie, excuse me. I'm going to click on the Find button, and I'm going to navigate to the folder where I've downloaded the data. Again, I have to drag the window over. And you can see there's a window that's opened up which has the deer data in it. Here's the real and the imaginary components. And you can see that this is a Q-band data set, and it has this artifact in it that often appears in Q-band data sets. So to take care of that, I'm going to go ahead and truncate 500 nanoseconds worth of data from the end of the data. So now this is the full data set. In this window here is the truncated data set. The data has been phase adjusted. The zero time has been set. And there's been an automatic generation of initial gases as to the background, the modulation depth, and also the parameters for a 1 Gaussian fit to this data set. Okay, so here's the background factor, the modulation depth, and then the mean of the Gaussian. To fit this data set, I'm going to click on the Fit button. That's going to adjust all of the fit parameters to give me the best fit to the data using a 1 Gaussian model. I can write that fit, the results of that fit, to my hard drive by clicking on the Write button. Now, to try a 2 Gaussian fit, I'm going to split this single Gaussian into two. And when I do that, you really won't see, it really won't be obvious that it's 2 Gaussians, but it actually has generated 2 Gaussians split from that one single Gaussian that was used initially to fit the data. I can now fit the data again using the 2 Gaussian model. I can save that fit to the disk. And I can look at the statistics from all the different fits, from the 2 different fits that I've done so far. And in particular, what you'll see here are these delta BIC values. And you can see for the 1 Gaussian fit, the delta BIC value is 5.4. It's 0 for the 2 Gaussian fit. The 2 Gaussian fit has the smallest BIC value, so therefore it should be the preferred fit. Here's where it tells me that that's the 2 Gaussian fit. N equals 2. I can close that window by clicking on Quit. I can once again split, I'm going to split here. The second Gaussian is both the broadest and has the largest amplitude, so it's a good candidate to be split. I'm going to run the fit for this 3 Gaussian model. And we can see that, and in particular, I can write this to the disk if I want to. I can save the file that has all that fit information in it. But instead what I'm going to do here is just look at the statistics, and you'll see that, in fact, for this 3 Gaussian fit, the delta BIC is positive, so it actually has a higher BIC value than the 2 Gaussian fit. The 2 Gaussian fit is preferred, and that's true even though the reduced chi-squared for the 3 Gaussian fit is lower. The reduced chi-squared is lower for the 3 Gaussian fit, but the BIC value is lowest for the 2 Gaussian fit. That's the model. The 2 Gaussian fit is the model that we prefer. Okay, the optimal model. These are the means of the Gaussians, their standard deviations, the background factor, an effective spin concentration, modulation depth. I can click on options, and in particular, it is possible to switch to different minimization routines, but I tend to think that, generally speaking, the interior point method works quite well. You could also try the global search method. It should probably take longer, but may in fact do a little bit more exhaustive searching. I can change the minimum and maximum allowed values for various different parameters by clicking on that limits button. I can run the confidence intervals, which are described in great detail in our methods in enzymology paper. Clicking on the confidence interval button. And I can write a file which contains all of the statistics information by clicking on that save button. I can sort by clicking on the heads of all these different columns here. I can also sort the values for the Gaussians by clicking on these buttons here. You may notice that the results we've gotten here for this 3 Gaussian fit are not quite the same that we've published in the paper. That's not entirely surprising when you are overfitting the data in particular, and this 3 Gaussian model does appear to be overfitting the data. When you're overfitting the data, finding the actual true chi-squared minimum can be rather difficult. And that is a situation where that global search can be very helpful. So if you notice, let's just go back and look at the statistics. The reduced chi-squared in the here, it's 1.0002. In the paper, it is slightly less than 1, and the delta BIC value for the 3 Gaussian model in table 1 is 8 point something. So let me just show you what can happen if we switch from the interior point method to the global search method. I'm going to close this, and I'm now going to run fit. Now this is going to take quite a bit of time. I'm going to start this, pause the video, and then I'll restart the recording in a few minutes. So we'll hit fit. This is a plot which shows me the plot of the reduced chi-squared as this global search is going on. The global search is a random routine, and so you can get different results every time you run it, but it's actually quite good and it's quite thorough, and it should eventually come up with a slightly better fit to this data. And I'm going to go ahead and pause the recording. Okay, so this global search has been going on for a few minutes. I could let it continue till it finally stops on its own. You can see that initially the reduced chi-squared values was above 1, and then for the last several iterations, it's gone down to 0.986 something. In my experience, it's not going to get any better, and I think this is basically the value that we published in the paper. So I can hit stop. This will take a little bit of time. Well, it didn't take much time there at all, but it can take a little bit of time for it to stop. And you can see that now we have an improved fit using this global search routine. But in particular, if I look at the statistics, you can see that, yeah, the chi-squared, reduced chi-squared did go down. The BIC value did go down, but the BIC value for the 3 Gauss fit is still well above that for the 2 Gauss fit. This value, the standard deviation, in this case for the second Gaussian, is highlighted in yellow because it's actually bumping up against the lower limit that I've set. I've set a half an angstrom lower limit on that standard deviation. You can see the amplitude of that component is only 2.6%, so it's very tiny. It's really not significant at all. If I wanted to see what happened if I reduce this lower limit and let this standard deviation value get even lower, I could go in here, edit the limits table. The width here for the second component is 0.5. If I change that to 0.05, now I'm going to hit initialize. You can see it's no longer highlighted because it's significantly above that lower limit. If I change back to the interior point method, initialize and fit, you can see that that component is just getting narrower and narrower. Again, that's a sign that we're overfitting the data. And if I look at the statistics, you can see that changing that lower limit has had a relatively negligible effect improving the fit, and it's again still the case that that second 2 Gaussian fit is preferred. I think that's all I have to say about fitting this data set using DD, and I will perhaps see you at the next video.